Right now, over the warm Pacific, a storm just doubled its power overnight. In a single day, its winds jumped by 90 miles an hour. Picture a race car's speed, added to a hurricane, while forecasters watched and could do nothing. We like to think we can see danger coming, but the deadliest storms hide their true strength until the last hours. A machine as wide as a country. An eye so small it could vanish inside one city. Calm at the centre, chaos in the ring around it. Ahead, we fly into that eye. We meet a storm the size of half of America. We find the tiny flash on a screen that warns scientists a monster is waking up. And we ask how strong these giants could ever grow. If wild science pulls you in, like this, and subscribe, stay close. We begin. A forecaster leaned toward her screen after midnight, and what she saw made her sit straight up. Far out in the western Pacific Ocean, a storm was doing something that should take days. It was doing it in hours. The night before, it had been a plain tropical storm, the kind that spins up and fades all the time. Now the numbers on her screen were climbing so fast she checked them twice. In a single day, the storm's winds jumped by about 90 miles an hour. Think of a car flooring it from a stop sign to full highway speed, then past a racetrack, then faster still. That is what the wind did. Scientists have a name for this kind of leap. They call it rapid intensification. When a storm gains at least 35 miles an hour of wind speed in one day, it earns the label. This storm blew past that mark and kept going. Why does that scare the people who study storms? Because speed like this steals time. A slow storm gives a coastline days to get ready. Families board up windows, buses carry people inland, boats come off the water. A storm that explodes overnight can turn from a threat people can handle into a killer while a city sleeps. The storm was named Dolphin, and by the time the sun came up it had teeth. Its winds had reached the range of a major hurricane. Out over open water, far from any island, it spun like a buzzsaw with nothing yet to cut. Forecasters kept watching, and the storm kept feeding. Every hour it pulled more heat and water up from the sea below. Every hour it grew taller and tighter and meaner. On the satellite picture, a small dark dot appeared at the very centre. That dot is called the eye, the strange calm hole that only the strongest storms build. We will climb inside it soon. Here is the part that keeps forecasters awake. A storm this powerful is still in a way hiding. From a coastline hundreds of miles off, the sky looks fine. The sea looks normal. There is no wall of black cloud on the horizon yet. The danger is real, and it is coming, though it does not announce itself the way people expect. By the time the outer clouds finally darken the sky, the worst of the storm can be only hours behind them. This is the heart of the whole story. The most dangerous super typhoons look harmless until very late. They build their strength far out at sea, in a place almost no one can see with their own eyes. The only way to catch them early is to read the tiny signals from above. A shrinking eye, a flash of lightning where there should be none, a pattern of clouds that whispers a warning long before the wind arrives. Over the next parts, we will learn to read those signals the way the experts do. We will find out what turns a plain patch of ocean storms into a monster the size of a country. We will meet the biggest and strongest storms ever measured, and we will stand with the scientists in that quiet room, watching the screen, feeling their fear grow. But first, we need to answer a simple question. What actually makes a storm a super typhoon? Somewhere over the tropics tonight, many storms are spinning, and only a rare few will ever earn the scariest name we give them. Start with the basics. A hurricane, a typhoon, and a cyclone are the same beast wearing different hats. The name just depends on where the storm forms. In the Atlantic Ocean, and near the United States, we say hurricane. In the Western Pacific, near Japan and the Philippines, we say typhoon. Near India and Australia, people say cyclone. Same spinning engine of wind and water. 3 names, 1 monster. Now most of these storms stay small. They spin up, dump some rain, and fall apart. To become something worse, a storm has to grow its winds. Scientists sort storms by wind speed on a scale that runs from Category 1 at the low end to Category 5 at the top. A Category 1 storm can snap tree branches and peel off shingles. A Category 5 can throw cars, flatten homes, and strip the bark off trees. A super typhoon sits at the very top of that ladder. To claim the title, a storm needs winds of at least 150 miles an hour, blowing steadily, not just in quick gusts. That is faster than a passenger jet as it lifts off the runway. In Japan, weather officials use their own top rank for these giants. They call the worst of them a violent typhoon, the highest level they have. Here is why 150 miles an hour is such a frightening wall to cross. Wind does not hurt you in a simple straight line. When wind speed doubles, the force it slams into a wall with grows 4 times stronger. So the jump from a strong storm to a super typhoon is far bigger than the numbers alone suggest. A little more wind speed means a lot more damage. A house that might survive a Category 3 storm can come apart at Category 5. The Western Pacific builds more of these top-tier storms than anywhere else on Earth. Every year, somewhere between 25 and 35 named storms form there. It is the busiest storm factory on the planet. In one recent year, the region produced a run of super typhoons in a single season, one after another, each one testing coastlines from the Philippines to Japan. And the strongest of them all reach a level that is hard to picture. Winds near 200 miles an hour. A centre of low pressure so deep it bends the sea itself upward. A wall of storm clouds taller than the peaks of the highest mountains. These are the storms that make forecasters lean in close and stop making small talk. A super typhoon begins as almost nothing. A loose knot of thunderstorms drifting over warm water, the kind of weather a sailor might barely notice. Something has to feed that knot and wake it up. Something has to pour energy into it hour after hour until it becomes a giant. That something is hidden below the waves. It is the fuel that every super typhoon runs on, and without it, not one of these storms could exist. To understand what forecasters fear, we first have to look at what these storms eat. Reach your hand into a tropical sea in late summer, and it feels like warm bath water. That warmth is the whole secret. A super typhoon is, in plain terms, a machine that drinks heat from the ocean and turns it into wind. The warmer the water, the more fuel the storm has to burn, and these storms are picky eaters. They need the surface of the sea to be at least 80 degrees Fahrenheit, about as warm as a heated swimming pool. Cooler than that, and the engine sputters and dies. Here is how the feeding works. The sun beats down on the tropical ocean all year, pouring energy into the water and storing it there like heat in a battery. When the air above gets stormy, that warm seawater begins to turn into vapour and rise. As the vapour climbs high into the sky and cools, it turns back into liquid and forms clouds. That change releases the heat the ocean had stored. The heat warms the air, the warm air rises faster, and it pulls even more moist air up from the sea to take its place. Round and round it goes, faster and faster, feeding on itself. Picture a spinning top that somehow finds a way to keep winding itself tighter. That is a growing typhoon. As long as it stays over warm water, it keeps pulling up fuel and spinning harder. Now here is a detail that makes forecasters nervous. It is not enough for the surface to be warm. The warm layer has to be deep. A storm churns the sea violently, dragging cold water up from below. If the warm water is only a thin skin over cold depths, the storm chills its own fuel and weakens. When the warmth runs deep, though, dozens of feet down, the storm can drink and drink without ever cooling the water beneath it. Those deep pools of warm water act like hidden gas tanks. A storm that crosses one can suddenly grow much stronger. This is exactly why the Western Pacific breeds such giants. Its waters are warm and deep across a huge stretch of ocean, wider than the whole United States. A storm can travel for days over that warmth, gaining strength the entire way, with nothing to slow it down. By the time it nears land, it has had a long runway to build into a monster. Warm oceans also explain a worry that has been growing among scientists. The seas have been heating up over the past few decades. Warmer water means more fuel sitting ready. Warmer water gives the storms that do form more room to climb to higher and higher peaks of strength. We will come back to that troubling trend later, once we have seen these monsters up close. For now, hold on to the picture. A super typhoon is a heat engine, and its fuel is the warm sea. Take away the warm water and the whole thing falls apart in a day. But warm water alone cannot build a storm. If it could, the ocean right at the equator, where the water is hottest of all, would spawn the worst storms on the planet. Strangely, it almost never does. The equator is one of the few warm places on Earth where a super typhoon simply cannot form, and the reason why is one of the strangest rules in all of weather. Right along the middle of the Earth, Where the ocean runs hottest, giant storms almost never grow. The reason is a spin you cannot feel, though the whole planet obeys it. Every super typhoon spins. That spinning is the thing that turns a messy blob of thunderstorms into a tight, powerful engine. Without spin, the warm, rising air just floats up and drifts away, and no monster ever forms. So where does the spin come from? It comes from the Earth turning beneath the storm. Our planet spins all the way around once a day. Because the Earth is a ball, different spots on it move at different speeds. Near the middle, at the equator, the ground races along at more than 1,000 miles an hour. Closer to the poles, it moves much slower. This uneven spinning gives the air a gentle nudge, curving winds to one side as they travel. In the top half of the world, moving air curves to the right. In the bottom half, it curves to the left. This nudge has a name. Scientists call it the Coriolis effect. Think of two kids on a spinning merry-go-round trying to toss a ball back and forth. From their seats, the ball seems to swerve off to the side every time. It flies straight, yet the spinning floor beneath them makes it look like it curves. The Coriolis effect is that same trick, played on the whole sky by the turning Earth. This gentle curving is what lets a storm start to rotate. As air rushes in toward a patch of low pressure, the curve bends all that inrushing air into a slow, wide spin. Once the spin begins, the storm can tighten it into the roaring wheel of a typhoon. Now here is the strange part. Right at the equator, the Coriolis nudge shrinks to nothing at all. There is warm water everywhere, plenty of fuel, plenty of thunderstorms. Yet the twisting force that would set them spinning is missing. Air rushes in and simply piles up with no swirl. So the hottest strip of ocean on the planet, the place you would bet on for the worst storms, almost never makes one. Typhoons need to be at least a few hundred miles away from the equator before the spinning force grows strong enough to matter. That is why the map of where these storms form has a curious blank band running straight through the tropics. The equator itself stays quiet, a calm road down the centre of the storm zone. Once a storm drifts far enough from that calm band, though, everything can come together. Warm, deep water below, moist rising air above, and now the steady twist of the spinning Earth to wind it all up. Give a cluster of storms all three of those gifts, and it can begin the change from gentle to deadly. Forecasters watch closely for that moment. They look for a loose group of thunderstorms out at sea and ask a simple question. Is this the one that will organise? Is this the blob that becomes a beast? Most of the time, the answer is no, and the storms fade. But every so often the pieces lock together, and a birth begins. So how exactly does a scattered mess of clouds pull itself into a single spinning giant? That change is one of the most stunning acts in all of nature, and it starts smaller than you would ever guess. It begins as a shrug in the sky, a loose patch of showers most people would sail right past. Out over the warm ocean, clumps of thunderstorms bubble up all the time. Most of them live for a few hours and die, but once in a while a group of them starts working together. Warm, wet air rises in the middle of the cluster. As that air lifts away, it leaves a little less air pressing down below. Scientists call that a patch of low pressure, and it acts like a drain. Air from all around rushes in to fill it. Remember the spinning force from earlier? As that air rushes inward, the turning Earth bends it into a slow swirl. Now the cluster has a centre and a spin. Weather experts give this baby storm its first title. They call it a tropical depression, a gloomy name for a hopeful little system just finding its feet. At this stage, the storm is fragile. Dry air can choke it. Strong winds high up can rip it apart before it ever gets going. Many depressions never make it past this point. But when the conditions are kind, the storm keeps drinking warm water and spinning faster. The rising air in the centre pulls up more and more moisture, building towers of cloud that climb miles into the sky. Once the steady winds reach 39 miles an hour, the storm crosses an important line. It gets a real name, chosen from a list prepared years in advance: Dolphin, Haiyan, Tip. From that moment on, the world starts paying attention, because a named storm has proven it can organise and grow. Picture a figure skater spinning on the ice with her arms stretched wide. When she pulls her arms in tight, she spins faster. A storm does the same trick. As its winds draw inward toward the centre, the whole system tightens and speeds up. The tighter it winds, the harder it pulls, and the harder it pulls, the tighter it winds. This runaway loop is the engine of every great storm. Deep inside, the structure starts to take shape. Bands of thunderstorms curl around the centre like the arms of a spiral galaxy seen from above. Between the bands, streaks of clearer sky appear. Rain hammers down in the curved arms and eases in the gaps, over and over as the whole pinwheel turns. By now, our little shrug in the sky has become a spinning giant hundreds of miles across, hauling millions of tons of water into the air every hour. It has a name, a centre, and a spin that grows fiercer by the hour. It has become a typhoon, and yet spinning alone cannot explain the raw power these storms reach. Something near the centre is acting like a furnace, pumping out heat and lifting the whole machine into a higher gear. To learn how a plain typhoon becomes a super typhoon, we have to find that hidden engine room and see what burns inside it. At the heart of every super typhoon hides a tall column of warm air, and that warmth is the reason the whole storm exists. We saw that these storms drink warm water and lift it into the sky as vapour. Here is the payoff. When all that vapour rises high and turns back into rain, it dumps out an enormous amount of heat. This is the ocean's stored sunlight being released miles above the sea. The heat gathers in the middle of the storm and builds a warm chimney that runs from near the surface up to the top of the clouds. Warm air is light air. As the core of the storm heats up, the air there gets lighter and lighter, and it stops pressing down as hard on the sea below. That drop in pressure at the centre is the key to everything. Air always rushes from high pressure toward low pressure, the same way it whooshes out of a popped balloon. The lower the pressure at the storm's core, the harder the surrounding air comes screaming inward to fill it. That screaming inflow, bent into a spin by the turning earth, is the wind. So the warmer the chimney, the lower the pressure, and the lower the pressure, the faster the winds. It is a chain that feeds itself. Warm water makes a warm core. A warm core deepens the low pressure. Deep low pressure speeds the winds. Fast winds churn up more warm water and lift even more heat. Around and around, tighter and tighter. This is why forecasters watch one special number as closely as the wind speed. They watch the pressure at the storm's centre. Weather scientists measure air pressure in units called millibars. Normal air at sea level sits around 1013 millibars. As a storm strengthens, that central number falls. A strong typhoon might drop to 950. A super typhoon can plunge below 900. The lower it goes, the deeper the storm's furnace is burning and the more violent its winds become. Think of the whole storm as a giant vacuum cleaner standing on the ocean. The stronger the motor, the lower the pressure inside, and the harder it sucks air across the floor. A super typhoon is a vacuum with an engine bigger than any machine humans have ever built, pulling in air across an area wider than many countries. The very strongest storms ever measured pushed this to extremes that stun the scientists who record them. Central pressures so low they seemed unreal. We will meet those record breakers soon, and the numbers will sound made up. They are real. For now, hold this picture in your mind. A super typhoon is a chimney of warm air standing on a warm sea, sucking the world inward and spinning it into a wheel of wind. The taller and warmer the chimney, the deadlier the storm. And right at the top of that chimney, at the exact centre of all this fury, something surprising happens. The air stops rising and begins to sink instead. That sinking air clears away the clouds and opens a strange calm hole straight down through the middle of the storm. Pilots who have flown into it describe blue sky above and a ring of towering white walls all around. Welcome to the Eye. It is the most peaceful place in the storm and one of the most dangerous spots on Earth. Fly into the centre of a super typhoon and the roar suddenly stops. One moment the plane is being hammered by walls of cloud and rain and wind strong enough to flip a truck. The next it bursts into an open, quiet space. The sky above turns blue, sunlight pours down, the wind falls to a whisper. All around, a ring of white clouds rises like the walls of a giant round stadium miles high. This calm clearing at the dead centre of the storm is the Eye. The Eye forms because of that warm chimney we just climbed. At the very top, air spreads out and some of it sinks back down through the middle of the storm. Sinking air dries out and clears away clouds, punching a clean hole straight through the heart of the monster. Inside that hole, everything goes still. The stillness is a trap. People who live through super typhoons tell the same story again and again. The wind howls for hours. Roofs tear off. Then, all at once, the storm goes quiet. The rain stops. The sun comes out. Believing the worst is over, people step outside to check the damage or run for better shelter. That is the deadly mistake. The Eye is only the halfway point. The calm can last 20 minutes or an hour, and then the far wall of the storm arrives with no warning at all, hurling wind from the opposite direction, often just as hard as before. Sailors from centuries ago wrote of this false peace at the centre of great storms, baffled by the sudden blue sky in the middle of the sea's worst rage. Birds sometimes get trapped inside the eye, flying in circles within the calm walls, carried along for hundreds of miles because they cannot punch back out through the wind. The size of the eye tells forecasters a great deal. A wide, round eye, maybe 20 or 30 miles across, often means a big, steady, mature storm. But when the eye shrinks down small and tight, something more alarming is happening. A tiny eye can be a sign that a storm is about to gather itself and explode in strength. We will get to those pinhole eyes soon, and they are the ones that keep scientists up at night. From above, on a satellite picture, a clear round eye is a beautiful and terrible sight. It looks like a single dark pupil staring up from a swirl of white cloud, which is exactly why we named it the eye. The rounder and cleaner that pupil, the more perfectly built the storm and the more dangerous it has become. The eye itself is calm. The ring of cloud around it carries the true violence. Those towering walls hold the fastest winds anywhere on the planet, faster than a race car at full throttle. The calm centre is just the quiet heart at the middle of that spinning weapon. That ring has a name, and it is where a super typhoon does its worst work. Scientists call it the eye wall. If the eye is the calm pupil, the eye wall is the loaded gun wrapped around it. Step out of the sunlight with me, back into the storm, and let us stand at the edge of the most violent ring of wind on Earth. The most violent place on the entire planet is a ring of cloud only a few miles thick. Wrapped around the calm eye stands a towering wall of storm clouds called the eye wall. This is where a super typhoon keeps its fastest winds, its heaviest rain, and its greatest fury. If you could stand safely and watch it approach, you would see a solid grey-black wall reaching from the ocean up toward the edge of space, spinning past you at highway speed and beyond. Inside the eye wall, warm air shoots upward with incredible force. These are the strongest updrafts in the storm, columns of rising air powerful enough to carry water thousands of feet into the sky in seconds. That rising air is what keeps the whole engine running, and it is packed into this narrow ring. All the storm's power gets concentrated here, like sunlight focused through a lens into a single burning point. The winds in the eye wall of a strong super typhoon can top 200 miles an hour. It is hard to imagine what that does. At around 100 miles an hour, wind can lift the roof off a house. At 150, it can level weak buildings and toss vehicles. Push past 200, and it strips leaves and bark clean off trees, sandblasts paint from walls and turns loose boards, signs and roof tiles into deadly flying blades. In the worst storms, the wind scrubs whole buildings off their foundations until only bare concrete slabs remain. Remember how wind force grows much faster than wind speed. Double the speed, and the punch grows 4 times stronger, so the eye wall of a 200-mile-an-hour super typhoon hits about 4 times as hard as a 100-mile-an-hour storm, far more than the raw numbers suggest. That is why the difference between a regular typhoon and a super typhoon is measured in flattened towns. The eye wall is also where the rain comes down hardest. The rising air in the ring dumps water by the ton, and it can flood a coastline in hours. Between the punishing wind and the drowning rain, the eye wall is the single deadliest stretch of any storm. When forecasters talk about where a typhoon will make landfall, what they truly fear is the exact spot where that eye wall will scrape ashore. Here is a chilling detail. The eye wall can change its size. In the strongest storms, it can pull in tight and small, and when it does, the winds inside it spin even faster. A narrow eye wall wrapped around a tiny eye can drive the winds to their most extreme speeds of all. That is the terror hidden in a shrinking centre. When forecasters watch a storm's eye pull in tight and small on the satellite screen, they know the winds may be about to reach a savage new peak. A small eye ringed by a tight eye wall is one of the clearest danger signs in the whole science of storms. So what does it mean when that eye shrinks to a tiny dark dot, no wider than a small city? It means the storm may be entering its most dangerous phase of all. Forecasters have a name for that shrunken centre, and the sight of it on their screen sends a jolt of worry through the room. They call it the pinhole eye. When a super typhoon's eye shrinks to the size of a small town, forecasters stop what they are doing and stare. Most storm eyes are wide, 20 or 30 miles across, but now and then a storm pulls its centre in tight until the eye is only 6 or 7 miles wide, a dark dot no bigger than an airport on the satellite picture. Scientists call this a pinhole eye, and the sight of one sets off quiet alarm in every forecast room. Why the fear? Because a pinhole eye almost always means one thing. The storm is about to explode in strength, and fast. Think back to the spinning wheel. A tight small centre spins faster than a wide one, the same way a small tight whirlpool spins quicker than a lazy one. When a storm draws its eye down to a pinhole, the winds around that tiny centre whip up to their most savage speeds. Some of the strongest storms ever recorded had eyes you could have covered with a single small city. In the Western Pacific in the year 2026, one storm showed exactly this. As it blew up over the open ocean, its eye tightened to a pinhole only 6 or 7 miles wide. Forecasters saw that dot form and knew what was coming. Within a day, the storm's winds had climbed by almost 100 miles an hour, one of the fastest jumps they had ever tracked. The pinhole eye had told the truth before the wind ever did. Here is what makes these tiny eyes so tricky. A pinhole storm is unstable, like a coin spun on a table that starts to wobble as it goes. Its strength can swing wildly. It might peak at a monstrous level, then dip, then climb again, all within a single day. That makes it a nightmare to forecast. A family on the coast might hear that a storm is holding steady, only for it to blow up to a far higher level in the hours before it reaches them. This is one of the deepest fears in storm science. A pinhole eye can appear right before a storm makes landfall, giving people the least possible time to react. The storm that looked survivable at dinner can become a killer by dawn. There is one more clue hidden inside a pinhole eye, and only sharp-eyed forecasters catch it. When the eye is this small and this fierce, the storm's walls take on a strange and telling shape, leaning outward as they rise. That shape shows up only in the most powerful storms on Earth, and spotting it tells forecasters they are facing a true monster. Scientists gave that eerie, tilted wall shape its own name, drawn from a place we all know. And the reason a storm's walls lean outward like the seats of a great arena reveals something surprising about how these giants are built. They call it the stadium effect. Stand at the bottom of the eye of a great storm, look straight up, and you seem to be sitting inside a giant open-air arena built of cloud. The white walls of the eye wall lean outward as they climb, so the eye is narrow near the sea and much wider high above. Look upward and the walls curve away from you on every side, opening into a broad circle of blue far overhead. Those walls can rise 9 or 10 miles high, taller than a passenger jet ever flies. It looks so much like gazing up from the floor of a packed sports stadium that scientists named it the stadium effect. This is one of the clearest marks of a truly powerful storm, so it is worth understanding why the walls tilt out. Here is the simple version. Air in the eye wall is racing around the centre in a tight, fast circle. Fast-spinning air wants to fling outward, the way you feel yourself pushed toward the door on a sharp, speeding turn in a car. Down at the ocean surface, the storm forces that air into a small, tight ring against its will. But as the air rises higher and higher up the eye wall, the storm's grip loosens, and the spinning air is free to swing wider. So the ring of cloud grows bigger with height, small at the bottom, wide at the top, shaped like a bowl opening to the sky. The more sharply the walls slope, the more intense the storm usually is. A weak storm has a straight, sloppy eye wall. A savage one carves out that deep, clean arena shape. So when forecasters spot a strong stadium effect on images from a plane or a satellite, they know they are staring at a beast near the peak of its power. There is a haunting beauty to it. Pilots who have flown into these storms describe the moment they break into the eye and look up. Sunlight streaming down, a perfect circle of blue at the top, vast white walls curving away in every direction, sometimes lit gold and pink by the sun, lightning flickering deep inside the cloud. For a few minutes, they float through the calm heart of the deadliest machine on the planet, surrounded by a cathedral of storm, and then they must fly back out through the wall into the wind and dark, because that peaceful arena is ringed by the fiercest gusts on Earth. The stadium effect also carries a warning. It shows up most clearly in storms that are extremely strong right now, or that are winding up toward a peak. Paired with a pinhole eye, a sharp stadium shape is about as loud an alarm as the sky can send. It tells the experts that this storm has organized itself into a nearly perfect engine, wringing every drop of power out of the warm ocean below. So far, we have watched a storm build itself up step by step, tighter and stronger, toward that flawless, terrifying shape. But we have not yet faced the single most frightening thing a storm can do. It is the reason forecasters dread certain nights. It is the behaviour that can turn a modest storm into a super typhoon while a coastline sleeps, with almost no time to run. They call it rapid intensification. And once you understand it, you understand why these storms are so deadly. A storm can go to sleep at night as a nuisance and wake up as a monster. We touched on this at the very start with the storm that gained 90 miles an hour of wind in a single day. Now let us look it straight in the face, because it may be the most dangerous trick these storms have. Scientists call it rapid intensification. A storm reaches it when its winds speed up by at least 35 miles an hour in just one day. The worst cases blow past that, doubling their power almost overnight. Why does this terrify the people whose job is to warn us? Because warnings need time. When a storm strengthens slowly, forecasters can see it coming and tell a coastline to prepare days ahead. Rapid intensification erases that time. A storm that looks like a routine threat in the evening can become a coast-flattening giant by sunrise, with families waking to an emergency no one saw coming the night before. For rapid intensification to happen, the storm needs a perfect setup. First, very warm water and lots of it, running deep below the surface so the storm never chills its own fuel. Second, calm conditions high above, with no strong upper winds leaning on the storm and knocking it off balance. Those high winds, called wind shear, act like a strong crosswind shoving a cyclist off balance. Take the shoving away, let the storm stand up straight and true, and it can wind up with nothing to stop it. When every piece lines up, the results are stunning. In 2015, a storm in the eastern Pacific blew up so fast it reached winds of around 215 miles an hour, the strongest ever measured in that half of the world. It went from a plain storm to that peak in barely a day. The storm named Haiyan, which we'll meet in full soon, dodged every hiccup that usually slows a storm down and roared to a monstrous peak, almost without pause. Modern storms are showing this behaviour more and more. In recent years, forecasters have watched storm after storm blow up in the final hours before hitting land, exactly when people have the least chance to escape. That timing is the true nightmare. A slow, steady storm is frightening. A storm that detonates right at the coastline is far worse. Scientists have gotten much better at predicting where a storm will go. They can draw its path days ahead with real skill. But predicting how strong a storm will get, and how fast, remains one of the hardest puzzles in all of weather. A storm can look ready to explode and then fizzle, or it can look ordinary and then erupt. The gap between tracking a storm's path and guessing its strength is where the greatest danger still hides. That is why every early clue matters so much. A shrinking eye, a deepening low pressure, and one more signal, hidden deep inside the storm that scientists have only recently learned to read. It is a flash of light where there should be darkness, a burst of lightning buried in the eye wall right before a storm goes wild. For years, no one knew what that flashing meant. Now, it may be one of the best early warnings we have. Let us go find the lightning inside the storm. Deep inside a strengthening super typhoon, lightning sometimes flickers in a place it usually stays away from. You might expect the most powerful storms on Earth to crackle with constant lightning. Strangely, the inner ring of a typhoon, the eye wall, is often oddly quiet, with little lightning at all. The reason lies in how these storms are built. Lightning needs air to churn up and down hard, smashing ice crystals together to build up a spark, the way you build static by rubbing your feet on a carpet. Over the warm ocean, the up and down churning in a typhoon is smoother and gentler than in a land thunderstorm, so the eye wall often flashes very little. Which is exactly why a sudden burst of lightning in the eye wall grabs a forecaster's full attention. When that quiet ring lights up, it can mean the storm's engine is suddenly revving harder, throwing air upward with new violence, and that fresh burst of power often comes right before the storm's winds take off. Scientists have watched this happen in storm after storm. The eye wall stays dark and quiet. Then, over a few hours, flashes begin to pop inside it, again and again. Soon after, the storm's winds start to climb fast. The lightning acts like the flicker of a match held under the fuel, a hint that the storm is about to blow up in strength. Researchers are still working out how much we can trust this clue, though it may become one of the earliest warnings we have that rapid intensification is beginning. How do we even see lightning in the middle of an ocean storm thousands of miles from land? From space. Modern weather satellites carry special tools that stare down at the Earth and map every single flash of lightning day and night in real time. From a satellite parked more than 20,000 miles above the planet, scientists can count the strikes inside a storm, watching the eye wall light up flash by flash while the storm is still far out at sea. This is a brand new power. For most of history, no one could see the lightning buried in a storm hundreds of miles offshore. Now scientists watch it live on their screens, hunting for that telltale flicker in the eye wall that whispers a warning. A storm might look steady on every other measure, and then its hidden lightning starts to flare and the experts lean in because they know what may come next. Picture a doctor watching a heart monitor. For a while, the beat is calm and even. Then it quickens and jumps and the doctor tenses because that change means something is about to happen inside. The lightning in a typhoon's eye wall is like that quickening pulse, a sign of rising power deep within the machine. Put the clues together and you see how forecasters read these storms: a shrinking eye, a sharp stadium shape, a pressure that keeps dropping, and now a flurry of lightning in the eye wall. Any one of them is a hint. All of them at once is a scream. Yet even lightning is only one strange feature hiding inside these storms. Fly close enough into the eye of a true monster, and you might catch sight of something even stranger swirling within the calm center. Small, fast-spinning knots of cloud spinning inside the spin, like tiny tornadoes trapped in the eye. And they may be a clue to how the very strongest storms reach their peak. Inside the calm eye of the strongest storms, small whirls sometimes spin within the quiet. We called the eye a peaceful place, and mostly it is. But in the most extreme super typhoons, the calm hides a secret. Around the edge of the eye, small spinning knots of cloud can form, each one turning fast inside the larger spin of the storm. They look like little whirlpools drawn on the inner wall of the eye. Scientists call them mesovortices, which simply means small whirls. Picture stirring a cup of coffee. As the whole cup spins, tiny swirls appear and dance along the surface, spinning within the bigger spin. The eye of a super typhoon can do the same thing, throwing off small, fast whirls around its rim. From high above, on the sharpest satellite pictures, these swirls sometimes line up around the eye in a neat pattern, turning the round pupil into a shape with straight sides, like a triangle or a six-sided figure drawn in cloud. That is a haunting thing to see. A storm's eye that looks from space, like a spinning six-sided nut, instead of a perfect circle. The straight edges are the work of these hidden whirls, each one bending the eye wall as it spins past. Here is why they matter. Each little whirl carries its own patch of extra-fast wind. Inside a super typhoon that already has monstrous winds, a mesovortex can spin up a small pocket where the wind screams even harder than the storm around it. It is a burst of extreme wind riding inside an already extreme storm, like a rogue wave rising above the other waves in a rough sea. If one of these passes over a building, it can do damage far worse than the general storm would explain. These whirls also tell scientists something about how fierce a storm has become. They tend to appear in storms that are very intense and tightly wound. When forecasters spot that telltale swirling pattern around a storm's eye, or catch the eye taking on straight sides, they know they are looking at a storm running at a savage level of power. For a long time, these whirls were almost too hard to study. They are small, they hide inside the deadliest part of the storm, and no one wants to fly a plane straight through them. It was only when satellites began taking pictures every single minute, instead of every 15 or 30, that scientists could finally watch the swirls form and move and fade in real time. Faster pictures turned a blur into a movie. Now researchers can watch the eye of a monster storm shimmer and spin, tracking each little whirl as it races around the rim. Every new detail helps them chip away at the deepest question in this science. How and why do these storms reach the savage peaks they do? We have now stood at the calm center, walked the violent wall, watched the lightning flash, and seen the hidden whirls dance in the eye. We have learned to read the storm at its strongest. Even at full fury, though, a super typhoon can suddenly tear its own core apart and rebuild it from scratch, stumbling and then coming back even meaner. That strange, violent makeover is one of the most surprising things a storm can do. At the height of its power, a super typhoon can suddenly turn on itself and begin to come apart. It happens like this. A storm reaches a fierce peak, with a tight eye and a roaring eye wall. Then, far out from the centre, a second ring of thunderstorms starts to form, a new outer wall wrapped around the old inner one. Now the storm has two eye walls, one inside the other, like two rings drawn around the same centre. The trouble is, both rings are hungry for the same fuel. The wide outer ring slowly chokes off the warm, moist air that the inner ring needs to survive. Starved, the inner eye wall withers and collapses. As it dies, the storm's tight, fast core falls apart and the winds ease off. For a while, the monster actually weakens. Scientists call this whole process an eye wall replacement cycle. Think of a snake shedding its old skin. For a short time it is awkward and open to harm, caught between the old and the new. A storm in the middle of this swap is doing the same thing, trading its old core for a fresh one. Here is the twist that makes it dangerous. Once the outer ring takes over, it begins to shrink and tighten, just as the first eye wall did. It draws inward, spins up, and the storm often roars back to full strength, sometimes even stronger than before. The weakening was only a pause. After the swap, the beast comes back, now with a wider, larger eye and a broader reach of powerful wind. In the year 2026, one Western Pacific super typhoon went through this cycle over and over, again and again across many days. It would peak, swap its eye wall, sag, and then climb back up. Each time, forecasters had to guess whether the storm was truly weakening for good or just catching its breath before the next surge. That guessing game is exactly why these cycles are such a headache. Imagine you are warning a coastline. You see the storm weaken and think the danger may be easing. You tell people the peak has passed. Then the eye wall replacement finishes, the storm reforms, and it slams ashore at full fury after all. The brief dip in strength can fool everyone, right when clear warnings matter most. The replacement cycle also changes the storm's size, and size brings its own danger. A storm with a fresh, wider eye wall spreads its strong winds over a much bigger area. So even if the top wind speed dips a little, the storm can now punish a longer stretch of coast, push more seawater ahead of it, and stay dangerous for more hours. A bigger storm can do more total harm than a smaller, slightly stronger one. This is why forecasters never relax when a storm seems to weaken. They know the dip might be temporary. They know the eye may be about to reload. A super typhoon in an eye wall replacement is a fighter catching its breath between rounds, and the next round may hit harder than the last. So how do scientists watch all of this unfold, far out over an ocean where almost no one can go? A storm can be 1,000 miles from the nearest coast, hiding its shrinking eye, its stadium walls, its lightning, and its swapping eye walls under a shield of cloud. To catch these clues, we needed a way to see the storm from the outside and the inside at once. That story begins with an eye in the sky that never blinks. A weather satellite hangs so far above the Earth that it seems to stand still, staring down at the storms below. To watch a typhoon that is 1,000 miles out at sea, you cannot use your eyes from the ground. You need to look down from space. High above the planet, weather satellites float in orbit, each one parked over the same patch of Earth, turning at just the right speed to hover above one spot. From more than 20,000 miles up, a single satellite can watch an entire ocean at once. These machines take pictures of the storms below over and over, all day and all night. The newest ones can snap a fresh image every single minute. Play those minute-by-minute pictures in a row, and a still storm turns into a living movie. Forecasters can watch the eye open, the eye wall spin, the lightning flash, and the whole giant crawl across the sea in smooth motion. But here is the challenge. In the Western Pacific, where the biggest typhoons roam, planes almost never fly into the storms to measure them directly. The storms form too far from land, over too wide an ocean. So for these giants, scientists often have only the view from space. They must judge how strong a storm is by studying its picture alone without ever touching it. Amazingly, they can do this with real skill, using a clever method built decades ago by a scientist named Vernon Dvorak. He noticed that a storm's strength shows in its shape. The pattern of the clouds, the neatness of the spiral, the clearness of the eye, the coldness of the cloud tops, all of it hints at how powerful the storm has become. By matching a storm's picture against a chart of known patterns, forecasters can estimate its wind speed and pressure from space alone. Think of it like reading a person's face. A doctor can often tell a great deal about how sick someone is just by looking at them carefully before any test. Dvorak's method taught forecasters to read a storm's face the same way. A tight, round, cold-topped storm with a clean eye is very sick indeed. A ragged, lopsided one is weaker. The neater and colder the face, the stronger the beast. The coldness of the cloud tops matters most of all. The taller a storm's clouds climb, the colder their tops become, some reaching more than 100 degrees below zero. Satellites can measure that cold, and the coldest, highest cloud tops mark the most violent parts of the storm. On a forecaster's screen, those deadly cold spots often glow in bright warning colours, painting a map of exactly where the storm is meanest. For most of history, this eye in the sky was the only way to size up a distant typhoon, and it is remarkable. But reading a storm's face from far away can only tell you so much. To truly know a storm, to feel its pressure and clock its winds for certain, someone has to go inside it. In one ocean, they do exactly that. There are pilots brave enough, or perhaps wild enough, to fly a plane straight through the eye wall of a monster and out into its calm eye. They are called the hurricane hunters, and what they do is one of the boldest jobs on Earth. Some people spend their whole lives running away from storms. A small group of pilots flies straight into them on purpose. They are called the hurricane hunters, and their job sounds impossible. They climb into a sturdy aircraft packed with weather tools, and they aim it at the strongest storm on the ocean. Then they fly right through the eye wall, the deadliest ring of wind on the planet, and out into the calm eye at the centre. Once there, they circle, gather their readings, and punch back out through the wall again. On a bad day, they cross that violent wall 4 or more times in a single flight. The ride is brutal. Inside the eye wall, the plane bucks and drops as it slams through walls of rising and falling air. Loose gear flies around the cabin. The crew is strapped in tight, teeth rattling as the aircraft shudders through the worst rough air in the sky. Then, in an instant, they burst into the quiet eye. The shaking stops. Sunlight pours in. Blue sky opens overhead, ringed by those towering white walls. For a few minutes they float in the calm heart of the monster, before turning back into the fury. Why risk it? Because a plane inside a storm learns things no satellite ever can. The satellite reads the storm's face from far away and makes a smart guess. The hurricane hunters reach out and take the storm's true measure. They clock the real wind speed. They read the exact pressure at the centre. They find out precisely how strong the beast is, right now from the inside. That direct reading is priceless. When a forecaster knows for certain how low the pressure has dropped and how hard the wind is blowing, their warnings get sharper, and sharper warnings save lives. A guess from space might be off by a wide margin. A reading from inside the eye is the real thing. Every flight feeds fresh, true numbers into the forecast, tightening it up. Here is a hard truth, though. Most of these flights happen near the United States and the Atlantic Ocean. Out in the western Pacific, where the mightiest super typhoons prowl, the hunters rarely fly. The storms are too far out, over too vast a stretch of sea, and no fleet stands ready to chase them there. So the world's most powerful storms are often the ones we can measure the least, judged mostly by their faces from space. That gap is a real worry. It means our best guesses about the strongest storms on the planet can carry the biggest question marks. Two forecasters looking at the same distant super typhoon might rate its winds many miles an hour apart, simply because no one can fly in and settle the argument. So the hunters do something clever to reach where the plane itself cannot safely go. They bring extra help. They carry small, smart sensors that they drop from the aircraft, letting each one fall straight down through the storm, radioing back everything it feels on the way. These little falling probes can go places no pilot would dare, plunging into parts of the storm too violent for the plane. Each one is a tiny explorer sacrificed to science, tumbling into the heart of a monster and reporting back until the moment it splashes into the sea. They are called dropsondes, and they gather some of the most valuable numbers in all of storm chasing. A small tube tumbles out of the belly of a plane and falls straight into the worst storm on Earth. It is about the size of a fat marker pen and it is packed with tiny sensors. As it drops, a little parachute pops open to slow and steady its fall. Then it rides the storm all the way down, from the height of the plane to the surface of the raging sea, and the whole way it takes readings and radios them home. Scientists call this falling probe a dropsonde. What can such a small thing tell us? Almost everything a forecaster wants to know. As it falls, the dropsonde measures how warm the air is, how heavy the pressure is, and how much moisture is packed into each layer. And by tracking exactly how the little probe drifts sideways as it drops, using signals from satellites far above, scientists can work out the wind speed at every single height on the way down. One dropsonde slices a clean line straight through the storm, from top to bottom, and reports what it finds at each level. Think of it like a core sample. When scientists want to study deep ice or rock, they drill straight down and pull up a long column that shows every layer. A dropsonde does the same for a storm, giving a top-to-bottom slice of wind, heat, and moisture in one quick plunge. Drop several of them in different spots, and you can piece together a full picture of the storm's inner structure, layer by layer. These probes are cheap and made to be used once. The plane simply carries a rack of them, and releases one whenever the crew wants a fresh reading. Each one lives for only a few minutes, falling and reporting until it hits the ocean and goes silent forever. A single storm flight might release dozens of them, each giving itself up to map a different slice of the beast. The numbers they send back are pure gold. Remember that the true pressure at a storm centre is one of the best measures of its strength. A dropsonde released into the eye falls right down the middle and reads that pressure directly, settling the question a satellite could only guess at. When one of these probes reports a shockingly low pressure at the core, forecasters know at once they are dealing with a giant. All these readings, from the dropsondes, the hunter planes, and the satellites above, pour into powerful computers on the ground. There, the numbers feed enormous programs that try to predict where the storm will go and how strong it will get. The more real measurements the computers receive, the sharper their forecasts become. A dropsonde falling into a storm today helps warn a family on a distant coast tomorrow. It is a strange and beautiful chain. A tube the size of a pen, dropped into chaos, tumbling through screaming wind, whispering numbers back to a plane, which sends them to a computer, which helps a forecaster decide when to tell a city to run. A tiny falling sensor becomes a link in the effort to save thousands of lives. We have now gathered our tools. We can read a storm from space, fly into its heart, and drop probes down its throat. We know the calm eye, the savage wall, and the warning signs that make forecasters afraid. Now it is time to point all of it at the true giants, the record breakers, the storms so huge and so strong they rewrote what scientists believed was possible. And the first of them was a storm so vast it could have swallowed half a continent. In the autumn of 1979, a storm grew so wide it stretched nearly halfway across an ocean. Its name was Tip, and it holds a record no storm has beaten since. From one edge of its spinning winds to the other, Tip measured about 1,380 miles across. That is wide enough to reach from one side of the United States almost to its middle. If you set Tip down over the country, its winds would cover close to half of it at once, a single storm as broad as a continent. Picture flying a plane along the edge of Tip's winds and trying to circle the whole thing. Even at the speed of a jet airliner, that trip would take you several hours. Most storms you could cross in one. Tip was in a class of its own, a giant among giants, so large that smaller typhoons could have fit inside its outer bands with room to spare. It grew that big because everything lined up in its favour. Warm, deep water stretched for thousands of miles beneath it. The upper winds stayed gentle, and the storm simply kept feeding day after day, spreading wider and wider until it covered a chunk of the planet. Back then, in the Western Pacific, pilots still flew into these storms to measure them. Hurricane hunters flew into Tip again and again as it swelled, and what they found stunned them. The storm kept growing wider and its winds kept climbing, peaking near 190 miles an hour. It was both enormous and fierce at once, a rare and frightening pairing. Here is what a storm that big can do that a smaller one cannot. Size means reach. A compact super typhoon might batter a stretch of coast 50 miles wide. A monster like Tip can hammer coastlines many hundreds of miles apart at the same moment. Its winds, its waves, and its rains spread across an area so vast that no single warning could cover it all. Whole seas churned under one storm, and ships far outside what anyone would call the danger zone still found themselves fighting for their lives. Lucky for the millions of people in the region, Tip weakened a great deal before it reached land, and its worst fury stayed out over open water. Had a storm that size struck a crowded coast at full strength, the harm is almost too large to imagine. It would have been like 100 regular storms arriving all together. Tip teaches us something important about these giants. Wind speed is only one way to measure a storm's power. Size is another, and it matters just as much. Two storms can have the very same top wind speed, yet the bigger one can do far more damage, simply because it touches more of the world at once. When forecasters size up a threat, they ask not only how fast the winds are, but how far they spread. And Tip did not only set the record for size. As those pilots flew into its centre, their instruments read a pressure so low it broke every record on the books, a number that still stands today as the deepest ever measured in any storm on Earth. To understand why that reading terrified them, we have to look at what the lowest number in all of weather really means. Deep inside Super Typhoon Tip, an instrument read a number so low the crew checked it twice. We learned earlier that forecasters watch the pressure at a storm centre as closely as its winds. Lower pressure means a deeper, hotter furnace, and faster winds rushing in. Normal air at sea level presses down at around 1013 millibars. A strong super typhoon might drop below 900. Inside Tip, the reading fell all the way to 870 millibars. That is the lowest pressure ever measured in any storm anywhere on Earth, and it still stands as the record today. What does a number like that actually mean? Picture the air as an ocean we all live at the bottom of. The whole weight of the sky presses down on us every second, though we never feel it. Inside Tip's centre, a huge chunk of that weight had been lifted away. The warm chimney at the core had grown so hot and so tall that the air there weighed far less than the air around it. That is a hole punched in the ocean of the sky, and the whole atmosphere came rushing to fill it. The deeper that hole, the harder the air rushes and the faster the winds spin. 870 millibars is a pit so deep it drives some of the strongest surface winds our planet can make. It is the sky's version of water pouring down the steepest waterfall in the world. The bigger the drop, the wilder the flow. Here is a way to feel it. As you climb a tall mountain, the air pressure falls, because there is less air above you. To match the pressure at the centre of Tip, you would have to climb the better part of a mile up into the sky. Yet Tip's centre sat right at sea level. The storm had created mountaintop thinness of air down at the surface of the ocean, in the middle of a spinning monster. Nature almost never does that. This is why the pressure number can frighten forecasters even more than the wind number. Winds gust and swing and can be hard to pin down. The central pressure is steadier and truer, a clean readout of how deep the storm's engine is running. When a forecaster sees that number tumbling hour after hour, dropping past 900, heading into the deep and rare territory below, they know the storm is winding up toward the top of its power. For most of the strongest storms, we can only guess the central pressure from satellite pictures far above. Tip was different. Because planes still flew into Western Pacific storms in those days, the record low was measured by a real instrument dropped into a real storm, which is part of why it is trusted so completely. Someone was there, inside the beast, watching the needle fall. No storm since has matched that 870, but plenty have come frighteningly close, and one of them, decades later, would carry a pressure nearly that low straight into a crowded coastline, with results the world will never forget. Tip spared the land its worst. The next great storm we meet did not. It struck one of the most crowded places in its path at nearly full strength, and it became the deadliest wind of its kind in modern history. On a November morning in 2013, the strongest storm ever to strike land came ashore in the Philippines. It was called Haiyan, and in the Filipinas it was known as Yolanda. For days, forecasters had watched it cross the warm western Pacific, growing meaner by the hour. Unlike many great storms, it dodged the stumbles that usually slow a monster down. It never paused to swap its eyewall. It simply kept climbing, higher and higher, until it reached a savage peak. And then, still at that peak, it slammed into land. When Haiyan hit the coast, its winds were blowing near 195 miles an hour. No storm in recorded history is known to have struck land any harder. Its central pressure had plunged close to the deepest ever seen. The full force of an open ocean monster, the kind that usually spends its worst fury out at sea, came ashore over towns full of sleeping families. The city of Tacloban lay right in its path. Home to more than 200,000 people, it sat at the end of a narrowing bay in the worst possible spot. The storm's fiercest side, the part that pushes the water hardest, aimed straight at it. What came next was less like a windstorm and more like the sea rising up and marching inland. We will look closely at that wall of water in the next part because it, more than the wind, is what did the killing. For now, know this. The water rose as high as a 2-story building, in some places even higher, and it swept through the city in minutes. People clung to rooftops. Whole neighborhoods vanished. When the water pulled back, it left a ruin that shocked the world. More than 10,000 people are believed to have died. Hundreds of thousands lost their homes. For weeks afterwards, survivors searched for clean water, food, and any word of missing family. The scenes coming out of the region were almost too much to take in. A modern city turned to splinters by a single storm. Haiyan taught the world a brutal lesson about these giants. A super typhoon at sea is a scientific marvel, a beautiful and terrible machine to study from a safe distance. The same storm meeting a crowded coast at full strength is one of the deadliest events on Earth. The line between wonder and horror is nothing more than a stretch of open water shrinking away. It also showed why forecasters fight so hard for every hour of warning. In the days before Haiyan, officials moved hundreds of thousands of people out of its path, and that effort saved countless lives. Yet even a strong warning could only do so much against a storm this size, striking this hard, in a place this exposed. Some coasts are simply built where the sea can reach them, and no wall of sandbags can hold back an ocean on the move. And that is the piece we have not yet faced. Through all these parts we have talked about wind, 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 but the wind gets more credit than it deserves. In the greatest storms the true killer is quieter, heavier, and far harder to outrun. It is the water the storm shoves ahead of itself, and it is time we understood it. The deadliest part of a super typhoon is the water it shoves ahead of itself. When people picture a great storm, they picture screaming wind. Yet in storm after storm, the sea takes more lives than the wind. Scientists call this killer the storm surge. It is a great dome of ocean water lifted up and driven ashore by the storm, and it can flood a coast faster than anyone can run. Here is how it builds. As the typhoon roars across the ocean, its winds do more than whip the air. They push on the surface of the sea itself, shoving water forward in the direction the storm is heading. Hour after hour, over hundreds of miles, the winds pile that water up into a broad rising mound. The storm's very low pressure helps a little too, letting the sea bulge slightly upward beneath the calm centre. Together this makes a hill of water that travels with the storm. Out in the deep ocean, that hill is spread wide and stays fairly low, so a ship might barely notice it. The danger comes when it reaches shallow water near the coast. There, the rising sea floor squeezes the mound upward, forcing all that water to stack higher and higher. And if the surge funnels into a narrowing bay, the shape of the coast pinches it tighter still, driving it to terrifying heights. A gentle swell out at sea becomes a wall of water at the shore. That is exactly what happened at Tacloban. The bay narrowed like a funnel, aimed straight at the city, and the surge climbed as high as a 2-story house, close to 20 feet. It swept inland in minutes, carrying cars, boats, and whole homes with it. Water is heavy, far heavier than wind. A wall of moving seawater hits like a slow, unstoppable landslide, and it does not ease off after a gust. It simply keeps coming. This is why surge kills more people than any other part of a storm. Wind, you can hide from behind strong walls. Water climbs over the walls, fills the rooms, and rises toward the roof. People who felt safe in sturdy buildings have drowned where they stood, trapped by a sea that arrived in the dark and rose faster than they could climb. The height of a surge depends on many things: the storm's strength and size, the angle it hits the coast, the slope of the seafloor, the shape of the bays. A weaker storm striking a funnel-shaped shallow coast can push a worse surge than a stronger storm hitting a steep open shoreline. This is why forecasters study the coastline as carefully as the storm, mapping exactly where the water would go and how high it might climb. and there is a cruel twist waiting in the future. As the world's oceans slowly rise over the coming decades, every storm surge starts from a higher baseline. The same storm that flooded a city yesterday will reach farther inland tomorrow, simply because the sea it rides on begins higher up the beach. So the wind roars and the surge climbs, and between them these storms do terrible harm. Yet when the news announces a storm, it usually gives you a single number, a category, or a wind speed, as if that one figure captured the whole threat. That number can fool you badly. Understanding why is the key to surviving one of these storms. When a storm is coming, everyone asks the same question. How strong are the winds? It makes sense. Wind speed is the number we use to rank these storms, from category 1 up to a super typhoon at the top. It is simple, it is quick, and it sounds like it tells you everything. The trouble is, it leaves out most of the danger. That famous scale measures one thing only: wind. It stays silent about the water the storm will shove ashore, the rain it will dump, the size it will spread across, and how slowly it will crawl over your town. Two storms can wear the very same category label and yet threaten your life in completely different ways. Think back to what we have seen. A storm's surge depends on its size and the shape of the coast, more than on its top wind speed alone. A storm's flooding depends on how much rain it carries and how slowly it moves. A giant, soggy, slow storm rated a little lower on the wind scale can easily kill more people than a compact, fast, higher-rated one. The wind number tells you how hard the gust will hit a wall. It stays quiet about how deep the water will rise around your bed. History is full of this hard lesson. Some of the deadliest storms on record were far from the strongest by wind. They were simply large, wet, and aimed at low, crowded coasts. Meanwhile, a few fierce, tight storms with terrifying wind speeds have blown ashore over empty land and harmed almost no one. The number on the news and the danger on the ground are two different things. There is another trap hidden in the wind number itself. When it climbs, the danger climbs much faster. We saw that doubling the wind speed makes the force 4 times stronger, so the jump from one level to the next is far bigger than it sounds. A storm that is only a little faster on paper can be enormously more destructive in real life. The scale looks like a smooth staircase. The damage climbs like a cliff. This is why forecasters beg people to look past the single number. They would rather you asked a different set of questions. How high will the water get where I live? How much rain is coming? How big is this storm and how slowly is it moving? Am I in a low spot the surge can reach? Those questions map the real danger far better than the category alone. The best warnings today try hard to spell this out. Instead of shouting one number, they show maps of where the water will rise, how deep it will get, and how much rain will fall. They treat wind, surge, and rain as 3 separate threats, because that is what they are. A person can prepare for a storm properly only when they see the whole picture. We have now met 2 of those 3 threats up close, the shrieking wind and the climbing surge. The third one is the quiet giant. It arrives without a roar. It falls softly, endlessly, for hours and hours, until rivers burst and hillsides slide. In many of the deadliest storms, this is the part that catches people by surprise, far from any coast. It is time to talk about the rain. Long after the wind dies down, the rain keeps falling, and that is when the rivers turn deadly. A super typhoon is, at heart, a machine for lifting seawater into the sky. All that water has to come back down, and it comes down as rain, in amounts that are hard to believe. A single big storm can drop more than a foot of rain in a day, and the wettest ones can pour down 2 or 3 feet before they move on. That is a whole year's worth of rain for some places, falling in a matter of hours. Where does all that water go? It runs downhill into streams and rivers, and it gathers. A river can stay calm through the height of the wind, then rise hours later as the rain from upstream finally arrives, swelling it far over its banks. This is why floods can strike a town long after the storm itself has passed and the sky has cleared. The danger flows in from miles away, quiet and patient and rising. Mountains make it far worse. When a rain-heavy storm runs into high ground, the land forces the moist air to climb. As that air rises and cools, it squeezes out its water even faster, like wringing a soaked sponge. So the slopes and valleys of a mountainous coast can catch stunning amounts of rain, far more than the flatland nearby. Whole hillsides, soaked heavy with water, can suddenly break loose and slide. burying everything below in mud and stone. The slower a storm moves, the worse the flooding gets. A quick storm sweeps through and is gone. A storm that stalls over one area or crawls along at walking speed dumps rain on the same ground again and again, hour after hour, until the land simply cannot hold any more. Some of the most destructive floods in history came from slow, stubborn storms that sat and poured over one unlucky region for far too long. This is the part of a storm that catches people far from the coast off guard. A family living 100 miles inland might think a typhoon has nothing to do with them. No surge can reach them. The winds have faded to a breeze by the time they arrive. Then the river at the bottom of the valley, fed by rain from the distant mountains, climbs over its banks in the middle of the night and pours into their home. The storm reached them after all, carried by water instead of wind. Forecasters now treat heavy rain as one of the top dangers of any great storm, right alongside the wind and the surge. They watch how much moisture a storm carries, how fast it is moving, and what kind of land lies in its path. A wet, slow storm crossing steep, crowded hills can be a recipe for disaster, even if its winds never reach the highest ranks. So these are the three faces of a super typhoon's fury. The wind that tears, the surge that drowns the coast, the rain that floods the land far inland. Put them together in one giant storm aimed at a crowded shore, and you have one of the most dangerous events our planet can produce. Which brings us back to the present, and to a run of storms that has forecasters more uneasy than they have been in years. The season unfolding right now has been throwing these monsters at the Pacific one after another. Something about this year is different. This year, the Western Pacific has been building monsters at a pace that startles even the experts. The season began early and mean. Before spring had even arrived, the first top-level storm of the year had already spun up over the tropics. By April, a super typhoon named Sinlaku had exploded to winds around 185 miles an hour and crossed small islands in the Pacific, a fierce storm arriving far earlier in the year than these giants usually do. For a top-tier storm to appear that early is unusual on its own. Then they kept coming. Through the late spring and into summer, one powerful typhoon followed another. A storm named Bavi climbed to the highest level and pushed toward Asia. Another, named Dolphin, blew up over the open ocean into one of the strongest storms of the whole season. It is the very storm we met in the opening, the one that gained nearly 100 miles an hour of wind in a single day and grew a tiny pinhole eye. Dolphin did more than that. It threw eyewall replacement after eyewall replacement, tearing down its core and rebuilding it over and over across many days, keeping forecasters guessing the entire time. It weakened, then reformed, then weakened again, refusing to burn out. Count them up, and the pattern is hard to miss. A string of top-level super typhoons in a single season, several reaching the highest rank, several threatening land. That is a violent year by any measure, and it is not over. As these storms keep forming over the still warm ocean, forecasters are watching the horizon closely, wondering how many more the season has left to throw. None of this looks like random bad luck alone. When a season runs this hot, scientists start hunting for a bigger cause behind it, some deeper condition in the ocean and the air that is loading the dice. A single strong storm can happen any year. A whole string of them, arriving early and often, hints that the entire system is tilted toward making monsters. And this year, that deeper cause has a name that climate scientists say only a handful of times in a lifetime. Far across the Pacific, the ocean and the sky have slipped into a rare and powerful pattern, one that reaches all the way around the globe and stirs the weather everywhere it touches. It has warmed key stretches of sea, shifted the winds, and set the stage for exactly the kind of season we are living through. Most years the pattern is mild or absent. Once in a great while, it grows so strong that scientists reach for a special word to describe it. This may be one of those years. To understand why 2026 has been so fierce, we have to leave the storms for a moment and look at the giant pattern breathing across the entire Pacific Ocean. It is called El Niño, and in its strongest form it can reshape the weather of the world. Every few years, a vast stretch of the Pacific Ocean grows warmer than usual, and the whole planet feels it. Scientists call this warming El Niño. To picture it, start with how the Pacific normally works. Steady winds near the equator, called the trade winds, blow from east to west, dragging warm surface water along with them and piling it up on the western side of the ocean, near Asia. That is the usual setup, year after year. During an El Niño, those trade winds weaken. With less wind to hold it back, the warm water spreads out and sloshes eastward across the Pacific, like water tilting in a long bathtub when you stop pushing it to one end. Suddenly a huge belt of the ocean is warmer than normal, and a warmer ocean, as we know by now, means more fuel for storms. El Niño does more than warm the water. It also calms the winds high above across parts of the storm zone. Remember that gentle upper winds let a storm stand up straight and wind itself tighter, while rough upper winds tear it apart. So El Niño can hand storms two gifts at once: warmer seas to feed on and calmer skies to grow in. It also shifts where storms are born. During an El Niño, typhoons tend to form farther east, out over the open ocean, well away from land. That may sound safer, and sometimes it is. But it also gives each storm a longer runway of warm water to cross before it reaches any coast. More runway means more time to strengthen. A storm that forms far out east can spend many extra days feeding and growing into a giant. Now here is what makes this year stand out. Most El Niño events are mild or middling. Every so often, though, the warming grows so strong that scientists reach for a bigger name. They call it a super El Niño. In one of these, the stretch of warmed ocean climbs to extreme levels, far above the normal bump. A super El Niño like this has appeared only a handful of times in the last 70-odd years. It is a rare beast. This year, the Pacific has tipped into that rare and powerful state. The waters have warmed to levels scientists watch for only in the strongest events, and the season has behaved exactly as you might expect when the ocean is loaded with heat and the upper winds fall quiet. Storm after storm, many of them reaching the highest ranks, arriving early and often. So the fierce season we are living through is more than a random streak. It sits on top of a rare, planet-wide pattern that has stacked the deck toward making monsters. Warmer water, calmer skies, longer runways. Every ingredient a super typhoon craves, served up across the whole ocean at once. Yet even a super El Niño is only part of the story. Beneath the warm surface the satellites can see, there is a deeper kind of heat hiding in the ocean, one that has been quietly building for decades. It is the true hidden fuel of the strongest storms, and it may be the most important number in the future of these giants. To find it, we have to dive below the surface. The most important fuel for the strongest storms hides deep below the waves, where no satellite eye can see it. We have talked a lot about warm surface water, but the surface is only the top of the story. What truly powers the greatest storms is how much heat is stored in the whole warm layer of the ocean, reaching down dozens or even hundreds of feet. Scientists have a name for this buried heat. They call it ocean heat content, and it may matter more than any single surface reading. Here is why the depth is everything. Remember that a storm churns the sea violently as it passes, dragging up water from below. If only a thin skin of warm water sits over cold depths, the storm quickly stirs up that cold water and chokes on it, cooling its own fuel. But when the warmth runs deep, the storm can churn all it wants and still find warm water underneath. It never chills its engine, it just keeps drinking. Picture two cars, each showing a full tank on the gauge. One tank is shallow and runs dry in minutes, the other is deep and lets the car race for hours. From the surface, both patches of ocean can look equally warm. Below, one holds a small snack and the other holds a feast. A storm that wanders over a deep pool of stored heat has hit the jackpot, and it can blow up to a size and strength a thin, warm patch could never support. These deep, warm pools act like hidden batteries scattered across the ocean. When a storm crosses one, it can suddenly surge in power for no reason a surface map would show. Forecasters have learned to map this buried heat, because a storm passing over it often intensifies fast, exactly the rapid blow-up that catches coastlines by surprise. Now here is the part that worries scientists most. As the planet slowly warms, the oceans have been soaking up almost all of that extra heat, and much of it is sinking down into the deep layers. Year by year, the ocean's hidden batteries are getting fuller and running deeper. The extra heat mostly raises the ceiling. It gives the storms that do form more stored fuel to draw on, letting the strongest of them climb to heights that would have been rarer in the past. Scientists have measured deep hot spots in the ocean that can push a storm past what were once thought to be its limits, feeding winds beyond the top of the old scales. The warm surface starts a storm. The deep heat below is what lets a monster become truly monstrous. This is the quiet engine behind a troubling trend. Around the world, the very strongest storms appear to be growing stronger, packing higher peak winds and intensifying faster than they used to. The total number of storms each year has stayed fairly steady. It is the top of the range, the rare giants, that seems to be climbing. But that claim deserves a careful look, because measuring storms across the whole planet, over many decades, is a tricky business. Are the strongest storms truly getting stronger, or are we simply watching them more closely than we used to? The answer sits at the heart of one of the biggest debates in this science. Ask two storm scientists whether typhoons are getting stronger, and you might start a long argument. On one side sits a worrying pile of evidence. Warmer oceans hold more fuel, and simple physics says more fuel should allow stronger storms. When scientists look at recent decades, they find signs that the share of storms reaching the very top ranks has been creeping upward. They see more cases of rapid intensification, storms blowing up faster than storms seemed to a generation ago. And the deep ocean heat we just explored keeps climbing, loading the dice a little more each year. Put together, it paints a picture of a world where the rare giants are becoming a bit less rare. But good scientists push back on their own ideas, and here the pushback is strong. Measuring storms across the whole planet over many decades is genuinely hard. The problem is that our tools keep changing. 50 years ago, we had far fewer satellites and much of the ocean went unwatched. A monster storm spinning far out at sea might have been missed entirely, or its strength badly guessed. Today, sharp satellites watch every corner of the ocean every minute. So when we count more strong storms now than before, part of the reason may simply be that we finally see them all. The Western Pacific makes this even trickier. Remember that planes rarely fly into those storms, so their strength is judged from pictures in the sky. The ways of reading those pictures have improved over the years. A storm rated a certain way in the past might be rated differently today, using better tools, even if the storm itself were identical. Comparing old records to new ones is a bit like comparing a blurry photograph to a sharp one, and trying to say which person is taller. So the honest answer is a careful one. Most scientists agree that warmer oceans give storms room to grow stronger, and many see real signs that the strongest storms are indeed intensifying faster and reaching higher peaks. At the same time, they admit that our changing tools make the exact size of the trend hard to pin down. The direction seems clear. The precise speed of the change is still argued over. What almost no one disputes is the danger. Even if storms were not changing at all, the world beneath them is. Every year more people crowd onto vulnerable coasts. Cities grow larger and push closer to the sea, and the ocean itself is slowly rising, lifting the baseline for every surge. So even a storm no stronger than those of the past would do more harm today, simply because there is more in its path to harm. That is the sober truth behind all the record-breaking headlines. The storms may or may not be climbing quickly. The stakes beneath them are climbing for certain. And there is one part of the trend that frightens forecasters more than any other, a change in timing that could cost lives no matter how the big debate settles. More and more, these monsters seem to save their most explosive growth for the worst possible moment, the final hours before they strike land. The nightmare that keeps forecasters awake is a storm that waits until the last moment to become a monster. We met rapid intensification earlier, the trick where a storm's winds leap by dozens of miles an hour in a single day. On its own, that is frightening enough, but there is a crueler version. More and more often, storms seem to be doing their fastest growing right at the end, in the final day or two before they reach land, exactly when people have the least time to escape. Think about what that does to a warning. Imagine a storm sitting offshore as a middling threat. Officials look at it and judge that people have time, that the danger, though real, can be handled. Families decide to ride it out at home. Then, in the last day and a half, the storm crosses a patch of deep, warm water, the upper winds fall calm and it explodes. By the time it hits the coast, it is far stronger than anyone planned for. The people who chose to stay are now trapped, with roads jammed and the storm already at the door. This has played out again and again in recent years. Storms that looked survivable one evening arrived the next day as coast-flattening giants. The storm we followed from the very start of this journey did much of its wild strengthening far from land, giving forecasters a rare early warning. Others have not been so kind, saving their worst blow-up for the final stretch and leaving almost no time to react. Why would storms intensify right near the coast? Part of the answer is that the waters close to many crowded coastlines have been warming, handing storms a fresh burst of fuel just before they arrive. A storm that might once have weakened as it neared land can now find warm water waiting there and strengthen instead, right up to the final hour. The safe cushion that coastlines use to count on is thinning. This is where the science still struggles most. Forecasters have grown very good at predicting a storm's path. They can draw the line it will follow days ahead with real skill. Guessing how strong it will be when it arrives, and whether it will suddenly blow up at the end, remains one of the hardest problems they face. A storm can give every sign of exploding and then hold steady. Or it can look calm and then erupt in the last hours. That uncertainty, arriving at the worst possible moment, is the deadliest gap in modern storm science. The cost of that gap is measured in lives. Every hour of warning a family loses is an hour they cannot use to board up, pack up and reach high ground. A storm that strengthens slowly gives people a fighting chance. A storm that detonates on the doorstep steals that chance away. So forecasters pour their effort into closing the gap, hunting for any early clue that a storm is about to blow up. And that raises the question at the centre of their whole craft. Just how well can we predict these storms at all? How far ahead can we truly see where a monster will go and what it will become? The answer is a story of remarkable progress and of stubborn limits we are still fighting to beat. When forecasters look into a storm's future, they draw a spreading cone, wide with doubt. To predict where a storm will go, scientists feed everything they know about the sky and sea into powerful computers. The machines then work out step by step how the whole swirling system should move over the coming days. This is one of the great triumphs of modern weather science. Forecasters today can predict a storm's path 3, 4, even 5 days ahead, with a skill that would have amazed people a generation ago. But no single prediction is ever perfect. So scientists play a clever trick. They run the forecast many times over, each run starting with tiny changes to the numbers. The way the real air always has small wobbles we cannot measure exactly. Each run traces a slightly different path for the storm. When you draw all those paths on one map, they spread out like a tangle of noodles tossed on a plate. Forecasters actually call this a spaghetti plot. The spaghetti tells a story. When all the strands bunch tightly together, the forecasters feel confident, because every version of the future agrees. When the strands fan out wildly in different directions, they know the storm's path is genuinely uncertain, and they warn a wider stretch of coast to stay alert. The spread of the noodles is a map of doubt. From all those runs, forecasters draw the shape you often see on the news, a cone that starts at the storm and widens as it stretches into the future. The cone shows the range where the centre of the storm is likely to travel. It is narrow at the start, where we know the most, and grows fatter farther out, where the guesses spread apart. Small errors early on grow into big ones later, the way a tiny wrong turn at the start of a long trip can leave you many miles off course by the end. Here is the mistake people make with that cone. They stare at the line down its middle and think, that is where the storm is going, and if I am off to the side, I am safe. That is a dangerous misreading. The storm can track anywhere inside the whole cone, and often does, and the cone only shows where the centre will go. The storm's dangerous winds, rains and surge spread far beyond that centre, reaching well outside the cone on every side. Sitting near the edge of the cone is no comfort at all. For all this skill at predicting a storm's path, one thing still slips through the scientists' fingers. They can often tell you where a storm will go far better than they can tell you how strong it will be when it gets there. Predicting a storm's track has improved by leaps. Predicting its strength has crawled forward by inches. That gap between knowing the where and knowing the how strong is the frontier of the whole science. To close it, scientists have begun turning to a brand new kind of helper, one that learns in a way no ordinary weather model ever has. Instead of following the old rules of physics step by careful step, it teaches itself the patterns of the sky by studying decades of past storms. And it is already beating some of the finest tools we have ever built. A new kind of forecaster has arrived, one that learned the weather by studying the past. For most of history, weather prediction worked one way. Scientists wrote down the laws of physics that govern air and water, then used giant computers to grind through those laws step by step, pushing the current weather forward in time. It works, and it took decades of brilliant effort to build. But it is slow and hungry, needing some of the largest computers on Earth running for hours to make a single forecast. The new helper works in a completely different way. It is a form of artificial intelligence, a kind of computer program that teaches itself by example. Scientists fed it decades of past weather, every storm, every wind shift, every pressure change on record, and let it hunt for the patterns hidden inside. Nobody handed it the laws of physics. It simply studied what the sky did, over and over, millions of times, until it learned to guess what usually comes next. Think of it like a chess master who has never read a rulebook but has watched a million games. She could not recite the official rules, yet she has seen so many matches that she senses, almost by instinct, what move should follow. These new weather programs do the same with storms. They have watched so many that they can feel where the next one is likely to go. The results have stunned the experts. These self-taught programs can now predict a storm's path as well as the best old-fashioned models, and in some cases better. And here is the jaw-dropping part. Once trained, they run in seconds on a modest computer instead of hours on a giant one. A forecast that once ate a supercomputer's whole morning can now appear almost instantly. That speed means forecasters can run far more predictions, explore far more possibilities, and update their warnings much faster as a storm changes. Scientists stay careful, though, and wisely so. These programs are still young, and they can stumble in surprising ways, especially with rare, record-breaking storms they have seen few examples of. A program that learned from the past can trip up when a storm does something the past never showed it. So for now, forecasters use the new tools alongside the trusted old ones, letting each check the other. The machine that learned from history and the machine that follows the laws of physics work best as a team. Bit by bit, these new minds are helping close the hardest gaps, including the great puzzle of predicting a storm's strength, not only its path. Early signs hint that they may finally be nudging that stubborn problem forward. If they do, they could buy coastline something more precious than any wall or sandbag. Time, extra hours of warning, wrung from a faster, sharper forecast. We have now followed these storms from their birth to their fury, met the record breakers, traced the warming that feeds them, and watched the tools we use to predict them grow sharper than ever. Only one enormous question remains, the one scientists cannot stop asking. If the oceans keep warming and the fuel keeps building, just how strong could a storm one day become? Is there a ceiling at all? And what waits for us if a storm ever reaches it? There is a limit to how strong a storm can grow, and scientists have tried to calculate exactly where it lies. Every storm is a heat engine, and every heat engine has a top speed. For a typhoon, that ceiling is set mainly by how warm the ocean is, and how cold the high air above it gets. The bigger the gap between the warm sea below and the cold sky above, the more power the engine can wring out and the faster its winds can blow. Scientists call this ceiling the storm's greatest possible strength, and for any patch of ocean, they can roughly work out what it is. Under today's conditions, that ceiling sits somewhere around 200 miles an hour, give or take, in the warmest waters on Earth. A few storms have brushed right up against it. In 2015, a storm in the eastern Pacific reached winds of about 215 miles an hour, the strongest ever measured anywhere, coming close to the very top of what our current oceans can support. It was a glimpse of the ceiling itself. Here is the unsettling part. That ceiling is not fixed. Warm the ocean, and the ceiling rises. As the seas heat up over the coming decades, the greatest possible strength of a storm climbs with them. Storms that top out at 200 miles an hour today could, in a warmer world, have room to push somewhat higher. The roof over these monsters is slowly lifting. Now for a truly wild idea, one scientists explore mostly as a thought experiment. What if the ocean grew not just a little warmer, but scorching hot far beyond anything we see today? Picture a stretch of sea heated to bathwater warmth, and past it, perhaps by a giant asteroid strike or a monstrous volcano warming the water. In that extreme, the math says a storm could grow into something with no name in our records. Some scientists have called it a hypercane. A hypercane would be a super typhoon beyond all reason. Its winds might scream at hundreds of miles an hour, perhaps twice the fastest storm ever seen. Its central pressure would plunge far below any record. Its top could punch up out of the ordinary weather layer and into the edge of the sky, spreading a shield of cloud over a huge region. A A single one might churn for weeks and reshape the weather of an entire half of the planet. To be clear, no hypercane exists today, and none is expected in any normal future. It is a creature of extreme numbers, a way for scientists to explore where the physics finally breaks. Our real oceans, even warming ones, stay far, far below the heat such a storm would need. The hypercane is a warning drawn at the very edge of possibility, not a forecast. Still, it makes the point in the sharpest way. There is a ladder of storm strength, and we have only ever climbed its lower rungs. The monsters that have terrified us, the Tips and the Haiyans, sit far below the true theoretical top. That should humble us. The storms we call the strongest in history may be only a taste of what the physics of a hot ocean can, in principle, build, which turns our eyes at last from the storms themselves to us. Because whatever these giants become, they matter only when they meet people, and more people now live in their path than at any moment in human history. For all their power, these storms turn into tragedies only when they find people, and they find more of us every year. Look at a map of where super typhoons roam, and then look at where people live, and the two overlap in the most dangerous way. The coasts of the Western Pacific, from the Philippines and Vietnam to southern China, Taiwan, Korea and Japan, are home to hundreds of millions of people. Some of the largest cities on Earth sit right at the water's edge in the exact zone where these storms come ashore. A single well-aimed super typhoon can threaten more people than lived in the whole world a few thousand years ago, and those coasts are filling up fast. Every year more people move toward the sea, drawn by cities, ports and jobs. Towns spread onto low ground that a big surge could swallow. Millions now sleep within reach of the water in places that, a lifetime ago, held far fewer souls. So even if the storms themselves never changed at all, the number of people in harm's way keeps climbing. The rising ocean makes it worse. As the seas creep slowly higher over the decades, every storm surge begins from a taller starting line. A wall of water that would have stopped at the edge of a city in the past can now push deeper into its streets. The same storm grows more dangerous over time, without gaining a single mile an hour of wind simply because the sea it rides has climbed. Faced with all this, it would be easy to feel hopeless. But here the story turns, because people are far from helpless in front of these storms. The single greatest weapon against a typhoon is a warning. Every hour of notice a family gets is time to board up, gather what matters, and move to high ground. Warnings that once came a day ahead now come several days ahead, and they have already saved countless lives. We saw it with the great storms themselves. When officials moved hundreds of thousands of people out of a monster's path, many who would have died instead lived. Sturdier buildings, smarter escape routes, better maps of where the water will go, drills that teach families what to do, all of it turns a would-be disaster into something survivable. The science we have followed through this whole journey, the satellites, the hunter planes, the falling probes, the learning machines, exists for exactly this, to buy people time. That is the deepest reason forecasters watch their screens through the night, hearts pounding as an eye shrinks to a pinhole and the pressure tumbles. They are in a race against a marvel of nature. Every clue they catch early, every warning they send in time, is a chance for a family somewhere to reach safety before the wall of wind and water arrives. So we return, at the end, to that forecaster leaning toward her screen in the dark, watching a storm double overnight. She sees what we have now learned to see: the shrinking eye, the stadium walls, the lightning in the ring, and she knows what it means for the millions who lie in its path. The question that remains is the one she asks every season, and the one we must all answer together. As these giants grow, are we ready for what is coming? We began with a single storm exploding in the dark, and we end with a whole planet's worth of them, stirring under a warming sky. Think of how far we have travelled. We watched a shrug of clouds over warm water pull itself into a spinning giant. We stood in the calm eye and felt the false peace at its heart. We leaned into the eye wall, the most violent ring of wind on earth, and learned to read the secret signs that warn of a monster waking. The shrinking eye, the sloping stadium walls, the flash of lightning where there should be none. We met the record breakers, a storm as wide as half a continent, and another that struck land harder than any before it. And we saw the quiet forces that feed them all, the warm seas, the deep hidden heat, the rare and powerful patterns breathing across the ocean. Two truths sit side by side at the end of this journey, and they are hard to hold at once. A super typhoon is one of the most beautiful things our world can make. Seen from space, it is a perfect white spiral wrapped around a dark, watching eye. A work of terrible art painted by heat and spin and water. And that same beautiful spiral is one of the deadliest events on the planet, able to drown a city and erase a coastline in a single night. Wonder and horror spinning together in one machine. The trend is real, even where the details are still argued. The oceans are warming. The hidden fuel is building. The ceiling over these storms is slowly lifting, and the coasts beneath them are filling with people. More of us live in the path of these giants than at any time in human history, and the sea itself is rising to meet them. The storms of the future may test us in ways the storms of the past never did. But the same story holds our hope. In a single lifetime, we have gone from being blindsided by these monsters to watching them form from space, flying into their hearts, dropping sensors down their throats, and teaching machines to predict their every move. Warnings that once arrived too late now arrive days ahead. Every satellite, every brave flight, every falling probe, every clever new program exists for one simple purpose: to see the storm coming and to give people time to get out of its way. That is the real meaning of everything we have learned. These storms will keep coming. They may keep growing. Yet each thing we understand about them is a life we might save, a family that reaches high ground before the water rises, a city that empties in time. Knowledge, in the end, is the shelter that holds. So the next time you see that white spiral on a screen with its calm, dark eye staring back, remember what is hidden inside it: a heat engine drinking the sea, a wall of wind faster than any race car, a dome of water waiting to climb ashore, and remember too the people watching it through the night, racing to warn everyone in its path. The ocean is warm, the giants are stirring, and now, at last, you know how to see them coming.